How we doing, everybody? So right now we're going to cover 3.3. In 3.1 and 3.2 we talked about some other rules or formulas involved with derivatives. Today we're going to talk about the derivatives of trigonometric functions in particular. So one thing I want you to understand is, first off, we're starting off by looking at the function f of x equals the sine of x, right? But know that we can represent this in a similar way by either talking about the cosine, the tangent, or the inverse functions, the cosecant, the secant, and the cotangent. But if we remember, if we view those functions, they are continuous at every point. So a sine function, a cosine function, a tangent function, continues to go on and on and on and on and on. Yes, there are discontinuities involved in some of them. When we have asymptotes, or what it might be, one of those examples could be the tangent of that. But know that we can take the derivative, right? We can figure out what our function is going to equal as it approaches 0, or any value for that matter. So, as we go through this, we're just taking a look at the sine function. We see the sketch of the f of x equals the sine of x. And if we were to interpret that with the f prime of x as the slope of the tangent to the sine curve, in order to sketch the graph of the derivative of f, it looks very, very similar. The only difference here, we have the sine of x here, and then over here we have the derivative of it, and we notice that we have the sine of x, and it essentially looks like the cosine function when we take a look at it, right? So that's something to keep in mind. Now, when we're calculating the derivative, that the way that we learned how to do that was using the limit, and we can do that in the same way by simply substituting for f of x the sine of x, or for f prime of x the cosine of x, right? And as we go through here, we figure out and we can calculate some different rules and equations that fall true for the limit definition. So two of these four limits are very, very easy to evaluate. The first one is the limit as h approaches 0 of the sine of x is always going to equal the sine of x. And the limit as h approaches 0 of the cosine of x is always going to equal the cosine of x. All right, but we have a few more rules that are important to understand. The limit as theta approaches 0 of the sine of theta over theta is going to equal 1. Okay, now this is kind of a graphical proof of that. This is the evidence of it. If we were to do the sine of theta here, the sine is always the opposite over the hypotenuse, the opposite being BC, the hypotenuse being OB. So therefore, we can say that the absolute value of BC equals the absolute value of OB times the sine of theta, which would then in fact just equal theta. Okay. Some other proofs that we have going on here too. We can take a look at the tangent lines of a circle, and we can see that the length of the circumscribed polygon is as follows. So arc AB is less than the absolute value of AE plus the absolute value of EB. Okay. So what I want to move towards right now is some of these functions that are important for us to know. So these are things that we want to keep in our notes, and we want to apply them to the different limit questions that we have. So the limit as theta approaches 0 equals the cosine of theta minus 1 divided by theta, which would equal 0. So that's an important one for us to remember. The derivative of the sine of x is always going to equal the cosine of x. So the derivative of the sine of x equals the cosine of x. And furthermore, we can figure out the derivative here through the solution. So differentiate x squared times the sine of x. This is the product rule, right, of derivatives that we're working on here. And then from that product rule, we're also going to know our knowledge of what the derivative of the sine is, and we're going to need that in order to calculate it here. So it uses two specific rules. Another one, we have d dx, the derivative of the cosine x equals the negative sine of x, right? And we can apply that, in the same way. We also have the derivative of the tangent of x equals the derivative of the sine over the cosine, right? We know that's true because the tangent of x does in fact equal the sine over the cosine of x. And then we can go apply it to this particular problem here, okay? This is the derivatives of trigonometric functions that are important for us to know and remember. This is, we already talked about a couple of them. We talked about the derivative of the sine, the derivative of the cosine, but it falls, true. And this is something that we definitely want to memorize or have at our fingertips when we're doing these problems here. We're going to skip the velocity piece. So 3-4 talks about the chain rule. This is probably one of the most important rules in calculus that we're going to go over. So we're going to cover that in our next video.